Hey guys, so this time we're going to be talking about bond energies, bond enthalpies. This is one way that we can use to estimate how much energy a reaction is going to be releasing or absorbing. And we do that by taking advantage of the fact that different bonds have kind of an average energy associated with them. And remember that if we go through, if you remember, this little graph, um, this can help you remember, okay, if I break a bond, is that going to be releasing or absorbing energy? If I make a bond, is it releasing or absorbing energy? One way to think about it is like this. So this is where you have the bond, and over here is where you don't have the bond, right? So if I'm forming the bond, what's happening? It's going down. This is a negative number. So that means energy is leaving, exiting the reaction. It's an exothermic process. If I'm doing it the other way, I'm going from a bond and I'm breaking the bond, that means I'm going up this hill. This is a positive number. This is going to be energy is entering the reaction. So this is a endothermic reaction. We are absorbing things. One way to think about this conceptually is just think about magnets. Okay, if I have two magnets that are stuck together, I got to put in energy to pull them apart. Okay, but magnets, whenever they're coming together, if I just let go and have two magnets slam together, you hear a clack. You hear them kind of clack together. That sound of them clacking together is energy being released. So that's another way that you can think about bonds being formed. If bonds are being formed, magnets are coming together, you hear a clack, that is energy being released. Whereas if you're pulling magnets apart, you have to put energy into it to pull it apart. So into it means endothermic, which means your delta H here is going to be a positive number. Okay. So with that in mind, we have this big, huge table here of bond energies. How does this help us? Well, if we have, I'm going to use this example. If we have this reaction that's taking place, right, we can draw out the Lewis structures of these guys and that are, right here. I know that I'm going to have to break this HH bond, this hydrogen-hydrogen bond. And you can go through and look up the HH here. Found it. They even wrote it right here for us. So we know that I'm breaking this. If I'm breaking it, I'm going to have to put energy is going to have to be released. Energy is going to have to be put into the system for me to break it apart. So this is going to be a positive 436. Okay. Same thing with this fluorine gas. Fluorine gas, F2. I'm going to have to break this in order for this reaction to go forward. So that means this is going to be a positive 155 because I'm going to have to be breaking it, endothermic, positive. Now I have two HFs being formed. So this is the bond that is going to be formed. And so it's going to be 567. So this is being formed. So it's going to be, energy is going to be released. So this is going to be negative exothermic, negative 567. Now, there's two of them here. Since there's two of them, two of these bonds are going to be formed. Okay? So then I can go through and sum all of this together. If I go through and I sum all of this, it turns out to be negative 543 kilojoules per mole. All right, so now we know this is what how much energy should be gained or released, absorbed or released with this reaction. Since it's negative here, we know that it is going to be energy being released. It's going to be an exothermic process. So this is nice. This can at least tell us a little bit. Now remember, I said this is estimating. This is estimating what the reaction is going to do. But an estimate is pretty good. Okay, I can tell with this that energy is going to be released, and about how much. 543 kilojoules. This is going to be pretty exothermic. So this is definitely going to be some energy being released. If you were like a chemical engineer and you were coming up with a new process to do things, you might want to run through and do a quick estimation using bond energies to see, oh, okay, this is going to be exothermic, and it's going to put out 300 gigajoules of energy. And you're like, oh, I'm going to need to do something about this because it's going to put out a crap ton of energy. So this is going to be something that can help you moving forward in your career. All right. So let me go through, bring this down. There are some things I want to talk about. Let's kind of go through. Here we go. Let's look at number 2 here. Okay. This is going to help us kind of think about what is making and what is breaking. So my question is, what is making and what is breaking? With this, we know that this F bond is going to have to break. Okay. I know that this CC double bond is going to have to break. This CH bond, it doesn't need to break. It's not breaking. It's here at the beginning and it's here at the end. That's fine. Same thing with this guy. It's doing just fine. Same thing with all of these. All of those are fine. I don't have to worry about those. They're not making, they're not breaking, they're staying the same. So that's fine. Now what's being made? Well, this CF bond is being made, and this CF bond is being made, and this CC bond is also being made. Remember, there is a big difference between a double bond and a single bond. And remember, a double bond is actually a sigma bond and a pi bond that is taking place. So it's a sigma and then a pi bond going above and below. Very different. You can't just say, oh, a double bond is 2 single bonds. Doesn't work that way. Easiest way to handle it is just to, when you come up here to look at your CC double bond, this is if you break the entire double bond. Okay. So when you come back down here, I have broken a CC double bond, and then I have made a CC single bond. Okay. So I broke the entire CC double bond, and I'm making a brand new CC single bond. So what does that mean? So that means I'm going to need to break a FF bond. I'm going to break a CC double bond, and I'm going to make a CC single bond and a CF bond and another CF bond. Okay. That is everything that we're going to need to make and break. Awesome. So then I'm going to head up to my little chart here. I'm breaking these, so these are all going to be, move over. These are all going to be positive numbers because it is going to be, I'm going to have to put energy into it to pull these apart. And these are going to make, which means magnets are going to slam together and make a hair clack. So these are going to be not positive, it's going to be negative. There we go. So these are positive. These are all going to be negative. And we just start looking in on our chart. We're breaking this FF bond. There it is. So this is going to be positive 155. A double bond here. There's that. So this is going to be positive 614. A CC single bond is here. So this is negative 348. A CF bond is here. So this is negative 485. And there's two of them. Okay. And now we just need to calculate it. So 155 plus 614 minus 348 minus 485 minus 485. And if we sum all this together, it is negative 549. Negative 549. And this is kilojoules per mole. And this is, again, a pretty decent estimation of what this reaction down here is going to be doing. If we are going to be making this this reaction go through. So if I go through and I say, okay, if I start out with 10 moles of fluorine gas, how much energy is going to be put out? Well, you can actually now calculate that by using kind of your basic stoichiometry type stuff. All right. The rest of this I'm going to leave for you. These guys are, this is nice and simple. They've already given you the Lewis structures. Oh, so nice for these first 5. These bottom 8, though, you're going to have to go through, draw the Lewis structures, and draw out your Lewis structures, and then calculate what needs to be done. Okay. I'm going to just put this out here. Number 11 might be a little tricky. Or not a little tricky. It may just, if you want to actually draw number 11 out like you did up here with all of these guys, you have 7 O2. So that means you're going to have 7 oxygens around. It may just be easier to draw out your oxygen and then put like a little 7 off to the side to remind you, like, okay, there's 7 oxygens. I don't want to draw out 7 of these things. Yeah, there's that. So this is going to be the assignment for Wednesday. Yes, Wednesday. Yes, Wednesday. You should be watching this Tuesday night. And then we will be doing this Wednesday. All right, guys. I will see you guys tomorrow. If you have questions about this, we're doing it in class. So there we go. All right. Have a good one.